So hi, everybody. Thank you all for staying to the last session. Today, we're going to talk about data cleaning. And it's always hard to get the audience excited about data cleaning, but I'll try my best to do that. So data science is the million-dollar term that's describing a billion-dollar profession. I'm sure many of you in your job titles have data science or data scientist in it. So how does someone in the AMP lab, like me as a database student, think about how we should be supporting data scientists? Well, I like to think that we're building a scalable platform. We're building a highly optimized platform that you can customize for your job. So it's the right tool for the job, and we're just providing the platform. So it's sort of like this drill set. We're giving you the drill. We're giving you a lot of widgets that you can attach to this drill and solve your problem as you see fit. That's only the narrative. Imagine if you went to your hardware store and your hardware guy said, I'm going to give you this magical set of drill bits. But the only problem is there's one catch. You can use this anywhere you want, anytime you want, but you have to pick one uniformly at random. So this seems a little bit silly, right? Because that's not your problem. So this is obviously a facetious joke, and it's really not that good of a joke, but the basic idea is that many of these tools that we're building have very strict technical and mathematical conditions on when correctness is actually achieved. So I'm going to talk a little bit about how we can ensure that data science is reliable, especially in the presence of dirty data, and some of the challenges that we've been looking at Team SampleClean. So in a past life, I was a converted theory student to a database student. I just assumed away my problems. I just wrote this at the beginning of every paper. We assume IID random variables. And there is no Python function, make IID, right? Because when real data comes to you, it looks sort of like this. So this was a project that I was working on about a couple of months ago, where we had a researcher go out to the field in Uganda and collect a whole bunch of data, partially digitized and partially on paper surveys. So when she came back to Berkeley, we had some undergrad interns come in and transcribe those paper surveys. And we got data that looks like this. So I'm going to highlight this age column right here. Now, in the undergrad's defense, all the data is right there. The data is correct in some notion of correct, but it's not in a format that's conducive to analysis. Now, we basically had to spend night after night before this deadline to actually fix this data to make sure that we could actually do some analysis, like calculate average ages, because we had no idea whether there was some sort of a systematic bias, whether it was one undergrad that did this or whether it was multiple undergrads, and the data distribution. And now this simple problem of actively manipulating your data turns out all your statistical theory goes out of the window because you've now touched your data, you've modified it, and that's the problem. So this is like a broader issue in data science in general, because you just don't get a data set in front of you that's an IID sample. Data comes through some sort of a complex process. That you have an acquisition step, that this data is being collected through logs, it's being collected through some sort of an online portal, it's being collected through social media, or it's being collected through increasingly sensors or devices out in the real world. Then there's this ETL process. You're taking this unstructured data, you're taking some sort of empirical observation of real-world phenomena and controlling that into some sort of a structured data set. Then you have the process of cleaning. You have to identify errors, you have to fix these errors, and you have to make sure this data set is in some sense like analyzable. Finally, you have to have semantics for imputation. What happens if values are missing? What is a sensible value to put in as a placeholder? And only after that you can start thinking about the interesting problems. How do I construct features? How do I address any problems that I'm going to deal with this? And if there's any issue, you have to go back and fix it from the start. And this is really an iterative process. And it's only after that we can go from data to model. And a lot of our work in the AMP lab has been taking data to model really, really quickly. And we've spent a lot of time optimizing this last mile. And now when we've optimized these last miles, problems in this back half start becoming evident. So that's really going to be the point of this talk. I'm going to talk about how we've actually been trying to put statistical analysis to analyze situations when there are constraints on this back half. When there's basically constraints on the way that you're acquiring data, there are constraints on how much data you can transform, there are constraints on how fresh this data can be. For example, I might be able to only update my views every minute or every hour. And finally, what happens if there are interaction constraints? What happens if I can't actually arbitrarily open up these boxes due to privacy issues, due to other issues such as interface design and so on? So that's basically the high-level motivation of what the SampleClean project has become. And broadly speaking, it's a study of bad data. It's looking at how much good data do you need to make a decision with an epsilon accuracy. And there's a website, sampleclean.org. Feel free to take a look at this, and I'm going to kind of overview some of our work in the subsequent slides. So we've been publishing a lot of papers. There's a journal version of our paper just like overviewing the entire project, overviewing all of our results, and we have a whole bunch of recent results on this, and we have a new paper on data cleaning and privacy at Sigmod. I encourage you to email me if you want a preprint of that. So I'm going to kind of motivate our research. Like, what are the research problems that we're analyzing, and why is this interesting from a research perspective? And then I'm going to talk about the SampleClean data cleaning library, which is really useful to this audience because this is something that you guys can actually use. And most critically, it allows you to go from raw files to analysis under a single pipeline abstraction. And we can start thinking about end-to-end optimization and end-to-end bounds on your accuracy. And finally, I'm going to summarize with some of our ideas for the future. So let's go back to this example. Let's go back to this example and say what troubled us about this example. So if we look at it, the problem is that the errors in this data set are kind of hard to fix with a script, because you realize that the age column is corrupted in many different ways. It's not just like one error. There are all sorts of different types of errors manifest in this data, and we're going to have to write a program to handle this problem, like handle all of the corner cases. We're going to have to handle the string representations. We're going to have to handle 19.5, which is partially numerical, and so on and so forth. And this is what is actually a general principle in data cleaning, that this is a time-consuming process. It's very hard to enumerate all of the different cases that you have. And just in general, data cleaning is going to be expensive, and it's going to require manual effort. You're either going to have to spend time fixing this data and identifying errors manually and writing and going and developing software for this, or you're going to hand it over to people and say, hey, guys, just manually fix this. And this is not an insight that we've come up with on our own. There has definitely been a lot of interest both in industry and in academia about this problem. And there was a New York Times article about a year ago that said that data scientists actually spend 80% of their time just pre-processing data before any analysis can begin. And there's also a growing industry about this. Trifacta and Datatamer, I'm sure you guys have heard of these companies, spawned from academia and now making a big impact in terms of data science. So when we started talking to people, so when we started this project about 2 years ago, we went around and started interviewing people at different companies, and we realized that people don't actually work with their big, dirty data. They actually take small samples, and they prototype these changes on small samples of data. Now, this seems really sensible, because now you can take a small sample of data, you can do your really expensive data cleaning, you can enumerate all these errors, you can even do this manually if you have to, and test to see what your query accuracy is before you start getting into the big data sets. So you had this general principle where you had this big data, you take a small sample of it, and then you do some data cleaning, and then you have a query result. This seems fine, right? The problem is it's not quite fine. If I have a data set that looks something like this, and I have errors that duplicate rows. For example, this is a data set of restaurants, and I have 2 records that represent the same restaurant. Now, if I sample this data set, I'm going to have an overrepresentation of errors. My data set is going to have a larger percentage of duplicate records than it should. And this is kind of bug one that we noticed with this problem, that while people were doing this in practice, it was actually statistically not exactly correct, because a sample of dirty data that is clean is not the same as a clean sample of data, which is the semantics that the user actually expects. So part of our first project, and this was about 2 years ago, was how do we actually simulate sampling this hypothetical fully clean data set? And there's a lot of math behind this, but the basic idea is we can treat this probabilistically with and we can use a technique that is well studied in statistics called importance sampling, where we can actually reweight our results to simulate sampling from the clean data set. And we developed a lot of theory. We got bounds on this that basically said that if I need to get a query within some accuracy, this is how much clean data I need. This is the best rate I can get, finite sample and asymptotically. And I encourage you to take a look at our papers on this. So I'm going to highlight another interesting development over the last few years that really that we've been going beyond SQL analytics. We've been going beyond average, sums, and counts. And this actually poses an interesting challenge because now you have this whole training and testing loop. And this was the next problem that we chose to analyze about a year ago, was that when we started talking to people, again, after our first initial result about saying that how do we get disciplined statistical estimates on dirty data, we realized that it was really not the full story. What was kind of happening was something a little bit more complicated. There was this kind of feedback loop where people did a little bit of data cleaning, retrained their model, tested out on some holdout data, then did a little bit more of data processing, tested out on holdout data. Sound familiar? This is actually what almost every data scientist we talked to said that they did. And in the defense of the rest of the database community, everyone jumped on this. There are tons and tons of systems, and there are going to be more in the current year that basically build progressive data cleaning systems that realize that people clean a little bit of data at a time and then try to do analysis. And like many of these progressive cleaning systems even look something like this. They try to build these interfaces where you can actually go through craft transformations iteratively, and you can run queries to test how those transformations would affect this. So this seems sensible, right? But it turns out this actually has a really subtle statistical bug when you start going into these kind of models that we're considering machine learning. So now imagine we had a simple linear regression problem, and the data was just corrupted by some sort of a translation in one of the axes. So we have the red data that's bad data, and we have the green data that's a good data. We have the red model, this is the model trained on the dirty data, and we want to get the true model, the blue model, which is trained on the clean data. Suppose we clean a little bit of data. Suppose we clean 2 points and we fix those. We realize that the intermediate state, the intermediate model that we get is not only slightly incorrect, it's categorically incorrect. It's exactly the opposite of what we need to get. And similarly, if we just sampled this data and we said that, okay, let's look at only the data that we've cleaned, we realize that these samples are not able to support the high-dimensional models that we were talking about before. So what's going on here? This turns out to be bug 2. It turns out that existing models for progressive data cleaning that don't consider how the data will be used are categorically incorrect when it comes down to these kind of model training pipelines. So we started thinking about how do we fix this problem? How do we address what this problem is? How do we address this from a statistical perspective? And we realized that most models are trained, at least convex models, are trained with a technique called stochastic gradient descent. I'm sure you guys have seen the splash talk earlier today. And the basic idea is that you go downhill. And as long as you're on average in the right direction, you will kind of converge. But as a database person, we looked at this expectation of the gradient. We looked at this formula right up there and said, what does that look like? It's an expected value of a gradient applied to every point in your data set. This is just map reduced to us. It's an average over a transformation of all of our data. And we realized this is a problem we've solved before. We know how to answer average queries on dirty data, and we basically ported our theory here to show that we can actually devise an iterative loop that we call ActiveClean that replaces that clean, train, test loop that we saw before that allows for disciplined statistical estimation, that allows for guarantees that your model is not going to be wrong in the intermediate states. And we have a whole bunch of performance results to show that we can actually, by exploiting a little bit of the structure of this problem a little bit better than techniques like active learning and standard sampling, we can actually get almost orders of magnitude improvement in some cases in terms of convergence. So finally, that was kind of our theory section of this talk. I'm going to talk a little bit about how do we put this into practice, how do we actually let you guys use some of this theory that we've developed. So I just want to talk a little bit about the systems challenges. So I'm not a systems guy, but I'll try my best to talk about how hard it was to actually engineer these ideas. These ideas seem very straightforward, but in practice, making them work on Spark is actually a little challenging. So one thing we realized is that data cleaning happens at different time scales, especially when you get humans involved in the loop and you want some sort of an interactive data processing pipeline. The data scientist works at a different speed than the automated tools that we have on Spark. Spark can churn through terabytes of data in the order of seconds or milliseconds, but the data scientist can only review and request changes so fast. And dealing with these varying timescales is actually a challenging problem. And to make matters worse, a lot of these data cleaning primitives were actually UDFs. They're kind of these black boxes that we actually have very little visibility into. So that was kind of the challenge that we saw at the onset, and how do we actually start reasoning about what people are doing in practice and build software that is kind of safe for data scientists to use. So we built this framework that's called SampleClean. You can actually download it. It's on sampleclean.org. That is a data cleaning library. The first thing that we did is we tried to open up these UDFs. We basically built a model where we constructed a set of logical operators that we felt captured most of what we saw in data cleaning pipelines. And we basically said that these can be done with different physical implementations. Like the physical implementation is immaterial to us, but now that we know what's inside these UDFs, we can start optimizing over them, we can start reasoning about correctness, and we can start reasoning about ordering. The next thing that we started looking at is how can we actually build recommendation engines and tuning engines? How can we tell people what needs to be done in your data pipeline? What needs to be done? Are these the right parameters to choose? Are these safe? Are these going to cause some sort of a problem downstream? So basically, one of the abstractions that we built up, and this was especially in the context of crowdsourcing, that we realized that increasingly a lot of this data cleaning was being done by crowds and humans. We tried to make this asynchronous. We tried to make it so that the abstraction that the programmer declares is a pipeline, but it happens asynchronously. And basically, the cleaning step is going to happen in the background, and it's going to have a publication and subscription interface with any downstream analysis. But it turns out actually doing this on Spark is actually challenging. That Spark is not truly designed to do point updates and asynchrony. And I'm going to talk a little bit about the battle scars that I have on 3 different iterations because we rewrote the code 3 times, and I think this time is the charm. We got this kind of right this time. So our first iteration, we started using Tachyon. We stored our data as flat files, and we said that, okay, if we keep them in memory, then we can kind of do these byte-level updates to this data. It turns out this is not quite right. We needed the structure. We needed the SQL semantics. We needed to be able to push down our filters to the base data to avoid having to scan this entire data. So then we went to Hive. We said that, OK, what happens if we now scrap Tachyon, we start having in-memory tables in Hive that persist, we start doing some batch joins, now we can push down those filters. It turns out Hive is extremely slow, and this didn't exactly work out. And finally, in our current implementation, we've been using the latest and greatest version of the IndexRDD. And this turns out to have a lot more performance improvements. And there's some reasons why this is actually a good idea. So what we've been doing is we actually took apart these data cleaning tasks. We actually looked at real workloads, and we tried to understand, do we really have to solve the arbitrary asynchronous point update problem? And the answer is no. It's because most data cleaning operations follow the same pattern. This is kind of the anatomy of a de-duplication operation. The first step is that you take your data, you coarsely block it up into a small groups. Then within each one of these groups, you take this join. You try to look at all pairs within these groups. Finally, you basically say that most of the records are probably not duplicates, and there's a set of candidate duplicates. And finally, you basically say that there are going to be some candidates that are clearly duplicates. They're near exact matches. And what takes up most of your time is going to be these ones that are kind of ambiguous. So you realize this is actually a very, very small portion of your entire data set. For most data sets, the entire data isn't corrupted. It's only a small subset of records, and these are the records that cause the performance problem. So we really don't have to solve the arbitrary update problem. We really have to solve this problem where you're reading a lot of data and updating a few records asynchronously. And so this is what we took as an insight to say that we can use this IndexRDD structure because this is exactly the problem that IndexRDD solve. Just to kind of, I hate always putting up absolute numbers because I'm a theory guy, and to me, constants don't matter, but it actually turns out these have sometimes huge implications, and these are the 3 different things. Black is the implementation on Tachyon that was a few years ago. Yellow is the implementation on Hive that was like subsequently where you could push down these filtering operations, and blue was the implementation on the IndexRDD that we have recently. And this was an entity resolution task on this data set of restaurants. And we found that we got nearly like 6-7x improvement in some cases, especially when these kind of threshold values, so that means what we're considering duplicates, were small. So that means when that update set is small. In some other tasks, we saw nearly 2 orders of magnitude improvement over what your naive implementations were. So that's kind of interesting. And let's walk through a little bit about the API that we developed. So like I said before, it is the abstraction to the programmer is a pipeline interface, but it executes asynchronously. So this is the key idea is you can load a data set. We have loaders. We have an ETL framework that you can basically take in unstructured files, load them into structured data frames, and then we have this cleaning interface where you can pipeline and chain cleaning operations. So what does a data cleaning algorithm look like? You can actually specify a different from our library of data cleaning operations. We've pre-populated it with a subset of what we think is important, and you're free to add new operations to this pipeline. And so the basic idea is like we can say something like entity resolution is a data cleaning algorithm. And there are going to be two parameters, like a similarity function, so what we consider as two records being similar, and a threshold. So beyond that thing, these two records are going to be considered similar. Now, the cool part is that we've actually integrated this with a lot of the AM&P, the people of the AMP lab. We've figured out how to chain these operations up with also crowdsourcing primitives. So we can directly connect these operations just by, like this pipeline abstraction, send some of those hard tuples to the crowd to do this. So that it hooks up with Amazon Mechanical Turk or your internal crowd interfaces, and we have an entire framework just to allow you to do that. Finally, we've also, internally, we've built all sorts of tuning primitives where you can say that I don't want to actually set a threshold a priori. I want you to tune it and find the best threshold for me. And we automatically can do this tuning given some ground truth. Like you give me 5 or 10 examples and we'll learn how to do that on the fly. And obviously, you're not restricted to one algorithm. You can add multiple algorithms there and do as many or as complex things as you want. And the cool part about this is this pipeline interface allows us to chain up with our recent results, where we've actually said that let's build the entire stack, all the way from raw text file to the analytical query and to the machine learning model that you're going to train at the end of the pipeline. So we actually have support where you can do a whole bunch of cool things, and these are basically our 3 research papers, and you can create feature views of your data, and this will also give you some guidance on when these things work and when these things don't work. So just to wrap up, I just want to, if there's one point that you should take home from this talk, is we believe at Team SampleClean, statistical validity is a data management problem. That it's not enough to say that that's a statistical problem, this is what statisticians worry about. It is absolutely a data management problem. If we build bad tools, people are going to do bad things with those tools. And so that's kind of our motivation, that's our call to arms. And we realize that actually many of these bugs are subtle, they are often hard to understand, but the fixes for them are also relatively straightforward. They're actually relatively straightforward statistical fixes. They have clean analysis. And the fact that we can do this analysis also helps us give guidance to data scientists on how to design future pipelines. And we have a whole bunch of papers. Email me if you want to see any of these, any of the preprints we also have in progress. But that's basically it. And as a final wrap-up point, I encourage you to take our survey. We're conducting a survey about how data science and data cleaning is being done in practice. And we feel that never again should we publish so many data cleaning papers without an actually good model about how data cleaning is done. So you guys have an opportunity to really make an impact here. Tell us how you guys are doing data cleaning. Tell us how your analysis pipelines actually look like. And we're going to take this and try to analyze this problem and try to build this into our system. So thank you.
Are you familiar with Microsoft Prose project?
No, I'm
I don't know.
not familiar with it.
Okay.
Yeah. I think it's on. Oh, yeah. Any other questions? Yeah.
Perhaps you can address how your work builds on all the work that's been done, on relational data, sort of all the history. How does yours fundamentally build on that or differ?
So good question. So I think this is exactly the question that we should be asking, because the current view on relational data and correctness is being done in terms of constraints. The way that people look at the data cleaning problem, or have historically looked at the data cleaning problem, is I have a set of constraints, and how do I take my database from a state that it doesn't satisfy these constraints to a state that it does satisfy these constraints. What we're saying is that that's not enough. You need to go one step further. You need to say that what matters to the analyst is, are the queries I'm running on this inconsistent database and consistent database correct within some epsilon accuracy? That's basically our thing, that we widen the pipeline to also include the analyst query at the end of the pipeline. And that's what allows us to go from a combinatorial problem about constraint satisfaction to a statistical problem about distance from the correct answer. That's the short version of this.
Let's thank the speaker.